Hello, Calculus students and general seekers of truth. We will now consider this function, f of x equals e to the x. I've considered it, and we want to find an upper bound for the maximum error in approximating this function by its 8th degree Maclaurin polynomial on the interval -2 to +2. So let's first start out by writing the Maclaurin series for e to the x. Okay. So remember that e to the x is approximately 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial plus onwards and onwards and onwards. Okay. The general term for this is the integral of n equals 0 to infinity of the nth derivative. Well, we already know e to the x is its own derivative, and this is at 0. So we can simply say x to the nth over n factorial. Okay. So now what we want to do is use the, and we're not being asked to estimate anything. We're being asked to just find the error bound. If we were to estimate the e to the x function between -2 and +2. Okay, so let's keep in mind here t of 8. We're using the 8th degree polynomial of x is equal to 1 plus x squared over 2 plus x to the 3rd over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial plus x to the 6th over 6 factorial plus x to the 7th over 7 factorial plus x to the 8th over 8 factorial. Whew. And so on. Okay? But this is, if we were asked to do more terms or higher order, then we could just keep expanding this. But the e to the x Taylor polynomial is pretty straightforward to remember. But what about its error, okay, or the remainder term? Well, the remainder term is equal to exactly the nth plus 1 derivative, which in this case is the 9th derivative of the function at 0. No, I'm sorry, not at 0. Almost made a big goof there. At some mystery point C of x. Okay. Of x minus 0. The center here is 0, so I don't have to do minus 0. To the n plus 1 term, to the 9th, all over n plus 1 factorial. Okay. Which is equal to, now the 9th derivative of e to the x is beautifully simple. It's just e to the x again. Substitute c in there, so e to the c, and I'm going to put absolute values around here because the error is interested in the distances around. I should be more consistent with this. Okay, so the absolute value of the error is equal to the absolute value of this. And again, we're not worried about whether it's higher or lower. We just want to know how far away is it from the exact answer. Okay. So remember the 9th derivative of e to the x is e to the x. You're plugging c in there, so you get e to the c. X here is some term. Well, x in this case is going to be 2, at most 2. I'm going to leave this as x for right now, and then I'll fill it in the next step, times 9 all over 9 factorial. And we're estimating this for x between +2 and -2. Okay. So we want to set an upper bound for this. What is the largest possible value that this thing could be? Well, the largest possible value is the farthest end of the interval that we're dealing with. So if we put 2 in here, we could get that the error is at most e squared times 2 to the 9th over 9 factorial. Now, if we know the exact value of e, then we can take that square and we can just evaluate this out, and we'll get whatever the answer is. Okay, but let's pretend for a minute that we don't know the exact value of e, because if we did know the exact value of e, we don't need a Taylor polynomial to do any of this. So, assuming we don't know the exact value of e, okay, but we know that it is between 2 and 3. Okay, so we do know that e is somewhere between 2 and 3. Maybe we don't know what the e value exactly is, so it's 2.7 something. So it's between 2 and 3. So let's just say this whole thing here is less than 3 squared, or 9, times 2 to the 9th over 9 factorial. Okay, and evaluate this out, and we will get 0.0126 and some other decimals. Okay, so this is approximate. So the remainder term, or the error, is precisely equal to this expression according to Taylor's remainder theorem. We don't know what c is, but within this interval here, we can predict that it is no larger than e squared, okay, because the ninth derivative of e to the x is e to the x, or e to the c here. And the largest that this could be is if we put 2 into here. Right. Now, if you assume that e is not known, just pick a number that's bigger than e, in this case 3, and we work all this out. If e is known, if you assume you have modern day technology, then you can get this number to be a little bit smaller than before. And if you can think of some clever ways to get to even a tighter error bound, that's even better. But with 8 terms so far, we get down to within 1%, which is not great, but it's not too bad either, depending on the application. And as always in calculus, if you want more terms, if you want more accuracy, just do more terms. Okay. Alrighty. So I will end all these videos here, and I will have you do this on your own to see if you understand this works, and I will also have you do example 4 here on your own. I will make a video of it and post it at some later time, and I'll let you discover this for yourself. If you have the sine function and you take the remainder, and you take the remainder as n approaches infinity, and just see what happens there. Thank you for watching, and have a wonderful day.